Okay, in this video we're going to look at power and energy. Now we've already done a little bit of looking at this in mechanics, but we're going to look at it a bit deeper because what happens is when we look at some of these equations, it's nice to know that they actually do come from the same kind of origins and it all works. And this gives us a nice opportunity to do that really. So we've already studied power in the form of power is equal to an amount of energy transferred per unit time. And you know that unit quite happily as the watt, or the joule a second. Joule per second, sorry. Joules per second. Now, if we were to derive that to base units, then what we need to do, and you can always find the table of what base units are in your textbooks, one of the first spreads we came across. It's actually just going to do this to just prove a nice point more than anything else. So, deriving this to base units is all well and good. So, let's start out with the values that we know. So we've got energy, which is in joules, over seconds. Well, seconds is a base unit, so we can leave that one as it is, but what we have to do is we have to do something about this joules. Well, we need an equation for joules in terms of base units, and the way we do that is work done equals force times a distance. So that means a joule is a Newton meter. So we've broken this down into one base unit because meters is a base unit. Newtons, however, is not a base unit, so newtons we can do in terms of force equals mass times acceleration, which means that force, or newtons, is kilogram meters per second to the minus 2. And actually, if we combine these two now, what we can say is that 1 joule, or a joule, is equal to a kilogram meters squared per second. And that's essentially that. Now we can then input that onto there. We can go kilogram meters squared seconds to the minus 2 over seconds. Hopefully you can realise we can then, when you have an over second, that's like to the minus 1, so we can add another one on there. So that gives us kilogram meters squared seconds to the minus 3. And that is the base unit of power, otherwise equal to a watt or a joule per second. So in electricity, we can do something slightly different. In electricity, we can suggest that power is equal to, I'll do this in a different colour actually, I times V. Well, I times V are very, very different units than what we've got here. So how can this be the same power? Well, we can do this, and we're going to show you how it's actually exactly the same, and you can do this. This is the same power for both. So, I is measured in amps, which is a base unit. Amps is a base unit. Voltage, however, is not. Voltage is defined as an amount of energy per unit charge. Well, neither energy or charge is a base unit. So we need to break these up. Well, first of all, charge, well, Q is equal to I times T. So, is that now in base units? Well, yes it is, because time is in seconds, I is in amps, so we've got amp seconds. So we can then replace that with amp seconds. We'll do it towards the end. Energy from before, well, we've done energy already, but we'll go through it again just to make sure you can see the logic. Energy work done is an amount of force times the distance, which is a Newton meter. Force isn't a base unit, so F is equal to mass times acceleration, which is in newtons. That gives us kilogram meters per second to the minus 2. Combining these two units, replacing N with this value here, gives us a unit for a joule, which W in that case is kilogram meters squared seconds to the minus 2. So then let's combine everything we've seen right here. So we've ended up with amps, kilogram meters squared seconds to the minus 2. On the bottom, we've got amp seconds. And so what we can do here is we can go, right, well the A's cancel. And as before, if we've got an S on the bottom, that adds another minus number up the top there. So that leaves us with kilogram meters squared seconds to the minus 3. And look at that, it's exactly the same unit. Okay, so that actually is quite nicely proving that the power equations from mechanics that we were using, energy per unit time, and the power equation from I times V in circuits has the same base unit, and we are talking about the same value of power here in watts in both cases. So that's a really nice introduction to that. It actually gives you some practice and allows you to see the processes with deriving base units, which you are expected to be able to do, and we will give you some practice of that during some of your sessions that you have. Okay, so how do we take this a step further in electricity? Well, we take this a step further because power is not just measured in watts. It can also be measured in kilowatts. And the point being here is that this power can lead to a differentiation of the energy equations that link power. Because power is an amount of energy per unit time, therefore an amount of energy that's transferred using a device that has a power times by a time tells you how much energy that you would use. So in this case, most people are happy with the idea that a joule is equal to 1 watt times by a second. However, like I've already suggested, power can be measured in kilowatts, and we generally like to use a larger unit than seconds. We use hours, and so we have a new unit of energy, which is the kilowatt hour. And if you ask your parents or guardians, have you ever heard of the term kilowatt hours? It is the bane of their lives because it's what all their electrical bills and energy bills are measured in. You pay per kilowatt hour that you use, i.e. you're paying for a sum of energy that you're using in your house. So what we have here is an amount of energy which is a larger number. Well, how do we define a kilowatt hour? Well, we define a kilowatt hour by quite simply saying, well, what is it in joules? Well, what is a kilowatt hour in joules? Well, 1 kilowatt is 1,000 watts, and 1 hour is 3,600 seconds. So you should hopefully be able to show that 1 kilowatt hour is the same as 3.6 times 10 to the 6 joules. 3.6 megajoules. So in this case, it's quite nice to actually show that calculation there without too much difficulty. And that is generally the way we would define it. So it's the amount of energy transferred by 1 kilowatt by a machine or device that's delivering a power of 1 kilowatt over the course of an hour. And in this case, 1 kilowatt hour is 3.6 times 10 to the 6 joules.
So that's all you really need to know. Sometimes you get asked to do some little money calculations around this, but general mathematics will help you with that. And we can see some of those in exam papers and practice them in lesson as well. Okay, so have a look through that in your textbook. Make sure you're happy with any conversions that you might be expected to do. We'll have a go at some in class, like I said, as well. And that brings us to an end of the electricity topic. And we'll get plenty of practice and exam questions in, and we'll see if we can throw an extra video or two with some exam questions on here as well.